So yeah, I'm not going to ask you to calculate those. The means, mean, median, mode, fair game.
What about standard deviation? I don't understand it. I don't understand.
Okay, so standard deviation is, the way to think of that is the average amount that a person's in a population varies from the mean. So it's a measure of variance. The higher my standard deviation, the more scores vary. The lower the standard deviation, the more they're alike. The more they cluster around. So if I had people who are a lot alike, my bell curve could get narrow, but it would have the same shape. All right. So this, we'll come back to that if we need to. So one of the things that I ask you to look up in your preparation that's not in the book, I believe, is the law of large numbers. And the law of large numbers kind of comes down to this. The more people you add into a sample, the more the sample is going to represent the larger population. So if I measure you folks for, let's say, I don't know, something you could vary on height. That gets kind of tiring, but we'll do.
Favorite color.
Well, no, that doesn't work for us. I mean, it could, but it's not the best example. We'll just go with height. I want something that's kind of a continuous variable, so it's not categorical like colors of things. But let's say, well, we could do the balance thing, right? And so if I had you drinking grog and doing balance.
We should do that.
We should, yeah, good science, right? So I have 11 of you. My sample may not be that good for a variety of reasons. Number one, there's just not that many data points. Two, some of you are at an age where you're probably more career drinkers than other people in the environment. There's just a variety of reasons. But if I were to add more and more people, I would get a more representative picture of what's going on. So the law of large numbers is just basically telling us if we do enough trials, enough repetitions, if we get enough people, we're going to get a more representative sample. Now, that gets this idea of population and sample. A population is a group that includes every member of some type. So if I want to know about the population of AUM freshmen, I would have to go get a list of every single AUM freshman. It'd be every one of them. A sample is just a subset of a population. So it's some of the freshmen. Now, very often, we don't want to measure everybody in a population. Why? What's the argument against, if you're doing a study, measuring every person in the population? Take forever. Be a lot of work. And we try to be as lazy as possible as scientists. We want to get just good enough information to figure out what's going on and know better. It could also be very expensive. I mean, so you're doing a study on grog and balance in AUM students. Good heavens. You can't be buying everybody a cat. That's just a lot of booze. So we don't want to do that. So we want a sample of the population, but we want a sample that's large enough to be representative. That's the trick. Now, I told you a minute ago that, or several minutes ago, that the big issue becomes how big does your sample have to be? And the answer is the more variation you have, the larger the population has to be. The larger your sample has to be. So if you have a bunch of lightweights who pass out at one grog, you don't need a big sample. But if you have some people who drink pretty regularly, your sample is going to have to get bigger and bigger and bigger. Does that kind of help? Now, there's some ideas that we need to keep in mind about our samples in order for them to be good. One is the sample needs to be random. And to be a random sample, and this is an important piece of information, a random sample is one in which every member of the population has an equal chance of being selected to be in the sample.
Ooh. Say that again.
That. Oh, you mean the definition. A random sample is one in which every member of the population has an equal chance of being selected. We have to be careful about how we do our sampling, because otherwise we get non-representative samples. So, suppose I went and, so there's things like samples of convenience, we call them. I'm trying to do my study on grog and balance, and I happen to find the Christian Temperance Club. I doubt that there's one of those, but just work with me. Like the We're Not Going to Drink Club, right? And they're not going to be a very representative sample. Their alcohol tolerances, well, they may be hypocrites, but if they're really not drinking, their alcohol tolerance isn't going to be that good. Or I could accidentally stagger into, I should say stagger in, I could walk into the Drinkers Around the World Club, and they're going to do a different drink every, you know, they're military, okay, there you go. So they wouldn't be representative samples. And that would be a problem for us. And I'm missing my, oops, get me. Where are we at? Oh, this is killing me. Where's my picture? All right, hang on just a second here. This is not making me happy.
I think I figured out your blank sheets.
I'm glad you have.
Because it's this one here. It's not even.
Here's what I'm looking for. Oop. Well, some of this, the problem too is going to be that I continue to update them. So why do you want a representative sample? This is one of my favorite photographs of all time. Harry S. Truman. Drop the big one, right? If you look at this picture, what you will see is a headline. What does the headline say? Right. 1948 election. Dewey defeats Truman. You should find that a troubling headline. Dewey did not defeat Truman. Does anybody know the story on this? Great story. Back in the day, this instant publishing thing, like you couldn't follow Drudge from minute to minute to find out what the returns were from Wisconsin or wherever. It took a long time to get information out. And even though the paper might come out, say, at 5 in the morning, for it to come out at 5 in the morning, you'd have to print it, distribute it, write it, which means, realistically, sometime around 10 or 11 the night before, you're writing the headlines. So what do you do if you're a newspaper? You want to make some predictions, right? You want to guess. So, and if you think your guess is going to be good enough, you can go ahead and write your headlines. So back in 1948, the folks at the Tribune decided what they would do is call people the day of the election. Who'd you vote for? Dewey. Who'd you vote for? Dewey. Who'd you vote for? Dewey. Landslide sample. They're confident in their sample. Oops. Imagine 1948. What do you suppose is true about 1948 in communications? Does every 12-year-old have a cell phone?
Yeah. If they're cool, they do.
If they were time travelers, they might. Most did not, right? Did every house have a phone? Who would have the phone? The people with the bucks. Guess which party Dewey was in?
Rich people.
The Republican Party, right. So the paper's calling all the rich people and go, well, who'd you vote for? They're all saying Dewey. Their sample was not representative, clearly, of the population. It was a bad sample. Representative samples are just extraordinarily important because we're taking a small number of samples out of a population and we're going to generalize it to the larger population.
Is that Truman?
That's Truman, yeah. Lambda Chi.
Great looking time.
You bet. Drop the big one.
What is that?
Huh?
What's Lambda Chi?
It's a fraternity.
What's Lambda Chi? That's like asking what's ice cream. I don't know. Anyway, Harry S.
That's the one.
That's just wrong. Okay. So, representative sample. To be representative, the best way we can go about figuring out how to do that is to make it random. And there's another idea that goes along with random selection. It's a different idea, but very closely related. That we're going to get into when we're talking about experiments. It has to do with random assignment. So what we want to do if we're going to do an experiment, just kind of pre-shadow this, is we want to randomly select our sample of who's going to be in the study, and then randomly assign them to the treatment groups, whether the control group or the experimental group. That way, the best possible chance that any of these abnormal groupings exist get washed out. Okay, is everybody still with me? We got one more thing to do with our pirates, and edit, copy. All right. I don't think you have this sheet, but it's just 3 L brackets so far, so don't freak out. Oh, you do have it? Good. When I went this morning, I had to redo this sheet this morning because I lost it somehow. Made me sad. Let's see, Control V. Eek. All right. So there's our pirates, right? And let's look at, we're going to draw a bigger one of these. 0, 1, 2, 3, 4, 5, 6, and 7. And I'm going to move this over just a tad. There we go. And then 70, 60, 50, 40, 30, 20, 10. Oops. And again, I'm going to have to move these a little bit. Sorry about this. All right, so vertically I've got number of seconds. Laterally I have number of drinks. And what we can do then is, and don't draw this right there because what I'm going to do is and actually what I need to do is solid fill red. This will help. There we go. Clone. 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 All right. So if we look at pirate number 1, he had 4 grogs, right? And lasted how many seconds? So I could figure out a place here that's 55 seconds where 55 seconds and 4 seconds intersect. Okay, pirate 2 has what? 1 grog and lasts how many seconds? Like that. What's the next one?
3 and 56.
3 and 56. This isn't perfect, obviously, but you get the idea. Next one,
2.
2 and 65.
Yeah.
Okay, what's my next one?
2 and 60.
2 and 60. My next one?
6 and 45.
All right. Next one?
3 and 48.
I'm sorry?
3 and 48.
3 and 48, maybe around in there. Next?
4 and 38.
4 and 38. Next?
7 and 34.
34. Okay, and next?
5 and 25.
5 and 25?
Yes, sir.
Ship must have moved. Okay, and what else we got?
3 and 45.
3 and 45. Is that our last one?
Yes, sir.
Okay. Does everybody agree that's pretty much the way that would map out? This is called a scatter plot, and you're going to be asked about these perhaps on the exam. It's one of the things you're supposed to look at. So a scatter plot is a visual display of two scores. This is how correlations are derived. Now, these patterns that you see can take all sorts of shapes. Now, before I get too much into those, I want to... No, I better do that. This particular one, we would say, was a negative correlation. We would say that number of drinks and time you could balance are negatively correlated. So as you drink more, your balance would be worse. Now, so we get this kind of, negatives go like this. Now we could have a positive correlation where one score goes up, they would cluster trending up. So this is negative, this is positive, and we could have no correlation. This looks like somebody took a shotgun. Everybody tracking me? Now, a correlation, this is kind of interesting stuff, but I'm going to go through this reasonably quickly just so that's probably reasonably close to something like truth there. Oops. Let me pull this down. So a correlation, when people talk about that and they say, here's a correlation number, what's going on is mathematically or symbolic, essentially there's been this line that's been calculated right through the middle. How many of you have done this before in math? One of you, two of you? All right, so you, three of you, you know what this is, what's up with this. So there's this line in math. So if you remember slopes, that's what's going on. And the line represents the average. And what's going on is we're interested in every case, what we're doing is we have an average, and we're going to calculate how far all of these are from, and you get the idea, from the center line. And that's going to give us a value. And what we're eventually going to end up with is, a score that's going to range from plus 1.0 to negative 1.0. The score of 1, be it negative or positive, is a perfect correlation. A perfect correlation, every one of these dots would be on this line exactly. Be perfect correspondence. As we approach 0, they go further and further away. Now here's the funky thing. As we approach, so say we're starting at a positive 1, all of these, or a negative 1 in this case, all these numbers would be crunched in along this line. As we went to 0, they would scatter out, scatter out, scatter out, because there'd be no relation. What do you think would happen as we move back to positive 1? Or we move toward positive 1? They'd come closer, but what else? It'd move this way. I should do a little flash video on that. I just thought about how you could do that. So a positive 1 would move here. Then these groups, as we move towards 0, all of our scores scatter. But then, as we would go to 1 again, you would get a new line heading this direction for the positive 1. Who's confused by that? All right. Do you understand the graph in terms of how they got there? Do you understand that the closer they are to the line, the closer you are to a value of 1 or negative 1? Okay. Do you understand that as number of drinks increase, balance decreases? And that's a negative correlation. Suppose we did a different study and we were talking about hours, time studied, time used for study, and in this would do score on exam. Can you understand how it would be positively correlated? The more you study, the better you do on the exam. So that's versus that going this way. Do you understand that a perfect correlation is a positive 1 or a negative 1? Do you understand that? Okay. As scores get closer to this line, you approach 1 because it's a 1-to-1 correspondence. It's perfect. It's 100%. As these scores go away, I get more variance. That number becomes lower. It's less than 100%. So a 0.8 would be like an 80% correspondence. 60%, 50%, 40%, so on and so forth, to where there's no recognizable pattern. So from a positive 1 to, or in this case, from a negative 1 to nothing. But then in the case of the studies versus grade, you could start with a 0 correlation. If study made no difference, it just looked like a shotgun went off. But as if it were true that it helped, then the more study you did, the tighter your scores would get along that line.
So if all those dots on that line, it would be negative 1?
On,
No, it's negative because it goes this way.
Yeah,
It's positive because it's this way.
I
so
know. So if right there, if all those dots are on that line, it would be a negative 1?
on this line?
Yeah.
Yes.
Okay. Okay.
All right. So if we had, so you could have 0, if I could write, and that's no correlation. That's strong. Actually, that's a perfect correlation. And your book may give you different numbers. I can't remember exactly what they say, but essentially, by the time we get to a positive 0.8 or a negative 0.8 for most things, we say in social sciences that you have an interesting correlation. So you need at least an 80% correspondence for it to be interesting. That's just a rule of thumb. It could be different in different settings. There's also the notion of spurious correlation. And this is a different idea. You can have completely unrelated things that appear to be correlated. I can have high correlations between things that aren't important. So an example of this might be, and this is true, as number of students in a school district increase, so does the cost of liquor. That's a true, they're truly correlated. Does that seem meaningful? Okay, so you're going to go causal. It's like, yeah, little bastards make you drink. That's a possibility. What's really going on is there's a third variable that's related to those two. The two of those are not really related, but there's a third variable, and that is, as time goes on, you get the population growth. As time goes on, you get inflation. So you get the appearance that having more students in school is causing alcohol prices to go up. So my answer to that is get rid of schools because booze is too expensive.
What did the ST
That should be strong. It's my learning disability coming out ragingly at 9 in the morning. So in both cases, I'm meaning strong. Yeah, I know. I didn't schedule me for this time. No responsible administrator would have me teaching at 8, but they do.
Are you hungover?
No. No, sadly. Sadly not. I can't drink like my spirit would like me to anymore. It's more, I'm kind of like the old dog sitting on the porch going, kind of watch everybody drink. So you can get really questionable suggestions out of these sort of things. For example, imagine if you are a administrator for a large city and you have your spreadsheets, you love your spreadsheets. You might notice that when there are fires, you might discover a correlation between the amount of property damage that occurs and the number of fire trucks that are sent. And there's this positive correlation. The more fire trucks you send, the more damage there is. That seems counterintuitive, doesn't it? So clearly, you shouldn't send so many fire trucks. What's wrong with that logic?
It's kind of like you don't have the whole story right. Because more fire trucks are sent because there's going to be greater damage. They prevent worse damage from happening.
Yeah, it's a bigger fire. That's why more. But here's the thing. I mean, that's an obvious one. That's easy for us to get. But I guarantee if you watch the news, I bet if you watch a half hour of CNN, which I don't know, I haven't watched them so long because I can't take watching the fools. But if you can find anybody that actually does news, you'll find this kind of correlation. They'll go, a link has been found between this and this. And the immediate assumption is that you should reduce one of those things because it's causing the other. We don't know that. All we know is we have a correlation. As one thing goes this way, the other thing goes some direction. It is not causation. And I think one of the things I ask you to know about is causation. When we talk about causation, we're saying that a change in the one variable makes something change in the other. Other correlations that are spurious. Ice cream sales amongst the good people and drownings. As ice cream sales go up, drownings go up. So if you want to stop drownings, stop selling ice cream, right? It's the same logic. It's the same logic. It's the wet streets and rain problem.
I poured a bottle of water out yesterday, and I swear it started raining right after I did it.
There you go. There you go. So that's correlation. Correlation is a form of descriptive research because there's really no way of knowing for sure if there's causal directions. Now, they can suggest experiments to us. Now, if I want to know, is this correct? And I would suggest this is probably not far from the case. I could develop an experiment which would involve randomly selecting individuals so that everybody in the population has an equal chance of being in the study, and then randomly assigning people to groups. So the drunk has as much chance as being in the 7 grog group as he does the 3, the 2, the 1, whatever. And then give them their drinks, then time them. Now I can say with much greater confidence that I have a causal situation. All right, we're almost there. You've been very patient. I appreciate it. We've got 2 more pages, and then we're done with this chunk.
So we might get out of class early?
It could happen.
Quick question. What did you say correlation and causation?
Causation is not correlation is not causation. So I can say that there are 2 things that are mathematically related that they're correlated. They're coincidental. So they can be related. Often they are, but often they're not. Also, very often they're related to a third variable. So, for example, here's a kind of an interesting fact for you. Chances of you being involved in violence increases with the number of stories in the building you live in. More stories in the building you live in, the more likely you're going to be involved in violence.
That's correlation.
Very good. It's a correlation. What's the problem with that? The truth is they're related, but not causally. It turns out there's a third variable. So if you, in the notes I asked you about the third variable problem, the third variable in this case is what?
The more people in the building, the more likely you are to run into an altercation.
It's crowding.
Yeah.
Crowding is the problem. So that's what you're running into with that as a problem. And let me come back here just a little bit. I need to steal a picture. I need to highlight you. Copy. Okay, so I've got my bell curve, right? And what I want to talk about now is this notion of inferential statistics. And inferential statistics are used to infer from samples to populations. Because remember, we don't want to measure every possible person in the world. So we want to use samples, and we want to be able to say, are these 2 groups different? So imagine a study where we want to contrast learning or teaching styles. 2 ways of presenting information. I do one group and I get that graph that you see there. And I do a second group and I get another bell curve. Does this make sense to everybody? And let me see if I can get away with something. Hang on just a sec. Can't win. Can't win. Can't win, don't try. Grouping, ungroup, fine. And copy, paste. There we go. Don't freak out here, just hang on for a second. Trying to make my life just a little easier. There we go. And so we have these 2 bell curves, and I need to get rid of U2. How can I do that? Grouping, ungroup. All right. Oops, lost the edge of my curve. That's sad. Let's see if we can put that back. So the question is, are these groups the same or different? So imagine what we now have is they're on the same x-axis. We got the same numbers across here. Are these two groups different? Looking at them like this. You can from this because they're not even overlapping. So this would be like a mean of 25 and maybe one of 70. It's pretty clear these are different. Because remember, this slope here, the shape is telling us what our variance is. This,
You're saying like they were all part of the same graph, not two different.
yeah, I'm saying it's all one graph now.
Okay.
So we can tell, because this would represent the lowest score of this group, right? Does everybody see that? This would represent the highest score of this group. This would be the highest score of the low group and the lowest score. So they're not even overlapping. Clearly, these two groups are different. Now, very rarely do we get that kind of circumstance. In fact, when you get that, you don't even have to do a study, right? You pretty much know that some things suck. Other things are better. Now, what about these two characters? Are they really different? Because what's going on, if you think about it, is everything in this region that is shared, this entire piece here is an area where the two groups are indistinguishable. Does everybody understand what I'm saying? So now our problem becomes, what is the mean and what's the variance? Who does not see what I'm getting at? I'm betting somebody doesn't. Be the brave person. Are you tracking? All right. Do you understand the bell curve by itself? And you understand when we got them all on the same graph?
The highlighted part is the people that did the same?
Yeah, you couldn't tell the difference in the group. So what we have is here's a mean. Let's not do that in highlight or yellow. Sorry about that. So let's say this is our IQ here, and the mean here is 100, and these are 110. So there's our means. Now we know that some of the means are different, but we don't know if they're different enough to say, and here's the thing. When we talk about statistical significance, we're saying that with 95% confidence, these two groups represent different populations. They're functionally different. They're really, truly different. So this is where variance comes into play. And when we're doing an inferential statistic, I'm not going to do the math for you. We're doing an equation that takes into account means and variance to figure out if two groups are different. And this gets to the question you were asking. Can we have statistical significance but no functional significance? So can a group mathematically meet these requirements to say, yes, their means are different, but it not matter much? And the answer is yes. The answer is yes. You can get statistical significance. All it's saying is that if you did the study 100 times, 95 times you would get the same answer. Because remember, we're not looking at the entire population. We're pulling out a sample. And the samples can be wrong, and we know what the probability of those errors are. So this is what's going on when we're doing an inferential test. We're taking two bell curves, we're interposing them, and we're determining how different they are. And we can come back to that in a later idea. You won't go down in flames if you haven't grasped that perfectly yet. But understand that that's what's going on. We're trying to figure out if two groups are different or not.
So what do we need to know for our exam?
You need to understand what I just explained, that
What we need to know is it's finding out if two groups different.
right.
That's all we need to know.
If they're mathematic, well, I think a little more than that would be handy. But I'm telling you, you don't have to do the math. You don't have to. So we understand that these populations have central tendencies and they have variance properties. And the more variance we have within our groups, the harder it is to tell. So think about it like this. If I have two groups, each group has one person in it. One's 7 foot tall, one's 5 foot tall. How much variance do I have in my two groups?
Too much?
No, I have, each group has how much variance?
Too much.
2 feet?
No,
What do you ask?
they have no variance. I have a single subject in each group.
So there's no variance because there's only one person.
Right.
I got it.
So I bring them together. I don't need math to figure out who's the tallest. But suppose I start getting different height people in different groups, then it becomes harder to tell, particularly if I have some real goofy, 7-footers, and maybe I have lawn gnome sized people, and I mean it becomes hard to tell. So the more people I have, or the more subjects I have in a sample, the larger my sample has to be to cover for that. Now, the reason I tell you can have statistical significance without it being functionally important is this. If you understand how the equation works, you understand you can keep adding subjects until you can easily get. If I have groups that are too large, they can look more different than they are. It's kind of a funky thing. So the answer to that question is yes. Functional significance is, would it really matter? Is there an important difference in how this group performed versus this group? I don't know. Maybe there is, maybe there's not. But don't get caught up in the notion when somebody says, well, it's a statistical difference, to assume that necessarily it's a very big difference, because it may or may not be. Should be, but it gets into another thing called power, which we're not going to get into. So that is a walk through research methods. 2 days of epistemology and stats. Sorry, this is not the most exciting thing we're going to do this semester, but you need to understand this so that when we're talking about studies the rest of the semester, you can have some degree of sophistication in going, does the study make sense? Oh, actually, no, I've got one more thing. I apologize. But this will be pretty quick. Why is this? All right. My pages are all messed up. The last thing I want to talk about are experiments. So an actual experiment is different than research. So if I'm going out and seeing what the apes are doing, or what the Hells Angels are doing, or the Women's Auxiliary Club is doing, that's descriptive research. I can also do research that is correlational. I'm just seeing how two things are related. But the gold standard is an experiment. And an experiment has some characteristics that you are going to be responsible for. First, random selection. Which we've covered. Random assignment. Which we've covered. So, random selection, every member of the population has an equal chance of being selected. Random assignment, you have an equal chance of ending up in any of the various treatment groups. And so we'd have one group that's a control group, and you will see this on the exam, I promise, and at least one experimental group.
Is that part of random assignment?
Yes. Well, the assignment to them is. So I have to have at least two groups. One's a control group, and it gets no exposure to whatever I'm studying, and my experimental group gets some treatment. So if I want to look at level of alcohol versus balance, I have to have another group of pirates who don't drink. But I'm probably going to lie to them. I'm probably going to give them virgin screwdrivers. And that's kind of like the classic way to do that, is if you make a screwdriver right, you shouldn't know that there's liquor in it until you're staggering, right? So this is called a placebo, in effect. So there should be a placebo group. The experimental group is going to receive the treatment In this case, it might be one of 7 amounts of alcohol. But you, if you're a subject, should have an equal chance of entering into any of these groups. That's a requirement. And I'm going to, you're very, very likely going to see questions where I describe a experiment and ask you to pick out independent variable, dependent variable, experimental group, control group. Just expect that. The third thing that you got to have is manipulation and control of extraneous variables. And I'll come back to those in just a sec. The fourth thing you have to have is manipulation of the independent variable. And let's make a note to myself here. All right, so 3 kinds of variables here. The extraneous variable, those are variables that you're not studying but might impact the outcome adversely. So I want to control them. I want to hold them equal. So an extraneous variable in our pirate study might be body size. It would be silly to give a 400-pound pirate and a 100-pound pirate the same volume of alcohol and expect it to affect them the same. Everybody understand this? So what I might do, instead of saying number of drinks, it might be better to study blood alcohol content, so that is what's being varied. That would be controlling an extraneous variable. And we have to control them to understand what's going on. The independent variable is the variable of interest. It's the variable that we manipulate, that we move up and down. So in the case of our pirates, it's going to be the amount of alcohol, be it through number of drinks or blood alcohol level. In the studying experiment, it would be what? Remember we talked about, was studying and grades correlated? What would you manipulate in that case? Time studied, right. We would manipulate the amount of time studied. This would also lead us to the idea of the dependent variable, and that's the thing that you're measuring. So what are we measuring in the study experiment?
Amount of drinks versus...
No, the studying experiment.
Versus time.
Grade. Okay, no, so there's the only dependent variable in all that is the grade, performance on the test. In the pirates, the dependent variable is what? Balanced time. So the dependent variable is what's being studied. The independent variable is what's being manipulated. Extraneous variables are things that can influence in a bad way your experiment.
So the pirate, the dependent variable would be balanced time. The independent variable is the amount of alcohol given. And then your extraneous would be the body weight and things like that. Okay.
What's the independent variable?
The independent one,